Okay, we ever take another integral. This one's from the MIT integration bee, semifinals, round 2, problem 4. We have the integral of tan x times secant squared x times cosine 2x times e to the 2 cosine x dx. Okay, at first I found this one kind of frustrating because the thing that's sticking out and so obvious is we have tan x here. The derivative of that's secant squared x. So I was thinking, okay, make a u substitution. We basically have du, but then what do I do with all this stuff over here? Well, I don't know if you can make it work that way, but then I needed a different approach. And the other thing I'm noticing is we have cosine here, and we really have to deal with this. We can't really have cosine in the exponent on e. We have a cosine here, secant squared. This is the same thing as 1 over cosine squared x. Tan x, we have another cosine in here, sine x over cosine x. So my thinking is I just want to do a u substitution for cosine x, and then I'm thinking that's going to clean a lot of this stuff up. Now, if I do this and we take a derivative, the du is going to be minus sine x. And that's not bad because we have like a sine x right here. We can add a minus and bring a minus up front or something. So it seems like this could work. Now, the one problem I have is we want everything to be the same angle. Notice everything else is the angle is just x, and then here we have cosine 2x. Well, we have a few identities for that, and it seems like what would work best is if we do the one that's going to give me a cosine x because it's going to help with the u substitution. So what I did was I want to use this identity for cosine 2x and not one of the ones that contain a sine. So with everything we have here, let's just rewrite this. So first we'll have this minus sign we brought out front. I'm going to write out everything in terms of sines and cosines. So for this tangent, I'll write this as minus sine x times cos x. Then here we'll write this 1 over cosine squared x. Cosine 2x, I'll use this. So we're going to have 2 cosine squared x minus 1. And then for this thing, we're just going to have e2 cosine x dx. So then when we substitute, we're going to have our du right here. And so let's put this all together with the substitution. So we have minus sign out front. Here, let's put this together. So I can write this as 1 over u cubed. Here, this is going to become 2u squared minus 1. This will become e to the 2u, and then we have with this and this du. Well, I can multiply this out, distribute everything in, and create this as two integrals, separating it on this minus sign here. So for the first one, it's going to look like minus, distributing this in here, we're going to have a 2. U squared over u cubed, that's going to cancel. We're going to be left with just a u, and then we'll have this e to the 2u. For the second integral, this minus is going to cancel with this minus and give me a plus here. And we need a du, of course. So distributing in the e2u, this is going to be just 1 over u cubed e2u du. But then the trouble we have is, I think this one right here, I think this is impossible. I know usually the one we're used to seeing is e to the u over u, but then if you do a u substitution, you're still going to get something very similar to that. So I don't think we can do this. So I need to focus on this, and hopefully when I do this, I can find a way to deal with this or cancel something out. So for this integral over here, what I'm going to do is let's use integration by parts with the DI method over here to the right. So we'll have two columns, one to differentiate, one to integrate. In this case, I usually like integrating e to the 2u, but let's differentiate it this time. So we're going to differentiate e to the 2u, and then we'll integrate 1 over u cubed. Then differentiating over here in this column, first we're just going to bring a 2 out, so we get e2u times 2. Then we do it again, we bring another 2 out, we get 4 e2u. Integral of 1 over u cubed is going to be minus 1 over 2 u squared. Then integrate it one more time, we're going to be left with just 1 over 2u. Then we'll have part of our solution right here on the diagonals. We'll deal with this last part in a second, but then let's just write down what we have so far. What's going to happen is we have e2u in common here for both of them. And we also have a minus sign, so what I'm going to do is factor out e2u in front. Then what we're left with for this first one, we're going to have this 1 over 2 u squared. And then here for this one, the 2's are going to cancel. And so we're just left with plus 1 over u. And then this last row right here, this is going to be an integral. But what we can do, first of all, there's going to be some cancellation. So for this integral, 4 over 2, we can simplify that to just 2 over u e2u. But the thing to notice is this is basically, well, this is exactly what we have right here, right? So what we can do is kind of put a label on this. We'll call this thing I. We need to bring this in as an integral, but I'm just going to leave it as the label I. But here, this one with the minus sign is going to be minus I. And like I said earlier, this thing's impossible, so we needed this cancellation to simplify this thing, and we're just left with this piece right here. So then all I need to do is just back substitute in order to finish this off. So what's going to happen is we have minus E, bring in U as cosine, so we're going to have 2 cosine x. Then with cosines in the denominator, I can write it as secant. So like for this first piece, I can write this as half secant squared x. And this one's just going to be plus secant x. Add a plus c, and that's it. Okay, there you have it. Good one from MIT 2024. Thanks everyone for watching. Have a good day.